All right, what we're going to be doing next is to generalize the process that we have just seen. So far, we worked with a particular function, f of x equals x squared, and over the interval from 0 to 1. But we want to be able to find the area under any function, f of x, as long as it's a positive, continuous function that lies above the x-axis, and over any interval from a to b. So to that end, let's take a look at this graph. The red curve, let's assume that that's the graph of y equals f of x, and the function is given over the interval from a to b. And let me assign some points. Like for example, a I'm going to call x sub 0. The right-hand side of the first rectangle I'm going to call x sub 1. The right-hand side of the second rectangle I will call that x sub 2. And keep in this fashion, assume that we'll have n rectangles. So then the last one that uses b as its height, I'm going to call that x sub n. So these are called the partition points for the interval from a to b. Okay, so to find the area under that curve, first, once again, we're going to find the area of n rectangles. So we're going to use n rectangles in the beginning. And then we're going to take a limit as n goes to infinity. Now let's start with the base of each of the rectangles. I have a formula here. It says base is, the notation we use for that sometimes is delta x, an incremental distance in the x direction. And it says that it's b minus a over n. Let me first try to provide some explanation why that works. So for example, say we have an interval from 3 to 10, let's say 3 to 6. And let's say we're going to use 20 rectangles. What would be the base of each rectangle? First, you get the length of your interval. 6 minus 3 is 3. And you're going to fit 20 rectangles in that interval. So the base of each one would be 3 over 20. Similarly, if your interval is from a to b, then the delta x, the base of each rectangle, is going to be b minus a divided by n. Okay, then let's write an expression for the partition points. We call those x sub I. And for the right end sum, when you use the right end points, you really only need x sub 1 through x sub n, which are the right hand points of your rectangles. Now, the first one should, basically, you should always start, if you're going from a to b, you should always start at the left end point of your interval, and you will keep adding delta x to it. So if you add 1 delta x, you get to the next one. So for example, if I is 1, then you will get this one. You start it with x sub 0. Let's see, if I is 0, you are basically right at the point A. If I is 1, you add 1 delta x to A, so you're over here. If I is 2, you start at A, you add delta x, and you add another delta x, you end up over here. So as you can see, as you keep adding delta x to your left end point, you will keep getting the remaining points in that partition set. Now, to find the height of the rectangles, let's say height of the rectangles. Height of each rectangle. Remember that we had to plug in the partition points into the function. So for example, to get the height of the first one, I plug x1. Again, we're talking about right-hand sums. X1 into the function, I got a height there, thus I form my rectangle. To get the next rectangle, I plug x sub 2 into the function, get a height there, and that gives me the height of the second rectangle. So in general, to get a height of a rectangle, what we need to do is we need to plug in x sub I into the function f of x. So f of x sub I will give you the height of the ith rectangle. So to get the first height, you do f of x sub 1. Second one, you do f of x sub 2, etc. So once again, for the right sum, I goes from 1 to n. And now we're ready to put all the pieces together. So area estimated by using n rectangles and using a right sum equals. And from now on, I might abbreviate my notation. Usually, I'm going to be referring to the right sum just to make things easier, because we could have used the left sum, the midpoint sum. So I'm just going to pick one, and that will be the right sum. So I might drop this R notation. If I just say A sub n, please assume that to represent the area using n rectangles using the right sum. Okay, so the area using n rectangles. So we have to sum n areas of n rectangles. So that's I goes from 1 to n. In each case, I would need the base times the height. The base of each rectangle is delta x, and the height of each rectangle is f of x sub I, because we plug in the partition points into the function to get the heights. Now let's simplify that further. Like, we know what delta x is. Delta x is b minus a over n times f of x sub I. Now we know what x sub I is. So if you like, let's just plug that in there as well. X sub I is a plus I times delta x. As I goes from 1 to n, we now have area using n rectangles. Now, could I factor anything out here? Remember, the lower index of your sum gives you the variable. So here the variable is I. That means everything else can be treated as a constant. So that means the b minus a over n can be taken outside. So that's what I will do. B minus a over n times summation of f of x sub I, which is f of a plus I times delta x. As I goes from 1 to n, and to find the actual area, we just have to take a limit of the above as n goes to infinity. As we discussed, infinite remaining is the best option. You'll have no overflows, no underestimation or overestimation. So this will be the perfect fit of infinitely many rectangles covering that area. So the exact area will be limit as n goes to infinity of the above quantity, basically. You could just rewrite it, or I'm just going to take the shortcut and leave it with this. Okay, now let's do an example to see how we can use the ideas about this generalization technique. Okay, let's start with, once again, the example of f of x equals x squared, but this time a different interval. This time it's from 1 to 3, not from 0 to 1. Let's start listing the following, starting with delta x. Delta x is the base of each rectangle. At the moment, the assumption is we're going to have n rectangles. So the rule was b minus a over n, and in this case, that is 3 minus 1 over n, or 2 over n. Okay, now let's write the partition points. You must start at 1, that's the left-hand side of the interval, plus I times delta x. You keep incrementing it one base at a time. So this will be 1 plus, since delta x is 2 over n, it'll be 1 plus 2I over n. And now area using n rectangles, it should be the height of the rectangle times the base of the rectangle, and you can interchange. You could put delta x times f of x sub I, or the other way around. As I goes from 1 to n, let's fill in what we know. Delta x is, as we got above, 2 over n, and f of x sub I is, since f of x is the squaring function, just plug in x sub I into the squaring function, and that will be 1 plus 2I over n quantity squared, as I goes from 1 to n. Okay, this is the area using n rectangles, and if we want to find the exact area, you would just take a limit of this as n goes to infinity. Now, some of your homework questions, I will say, estimate the sum using 20 rectangles. And some of them I will say, find the exact area. If it says using 20 rectangles, basically, you can enter this into the calculator using the sum of a sequence command and just substitute n equals 20 into your expression. Now, the exact area usually involves more cumbersome calculations because you would then have to simplify this. You would have to use the summation, the sigma properties, and many of those formulas we've seen earlier today, and then at the end take a limit as n goes to infinity. For this question, I'm going to do it both ways, but again, read the questions carefully on the homework. Some of them will say use n equals 20. There you can use a calculator. Some of them will say exact area. There you have to do the messy work. Okay, so let's begin with part A, doing it for n equals 20. What is the area under this curve using 20 rectangles? All right, to enter this into the calculator with n equals 20, let's first rewrite the sum with n equals 20. So we're going to go I from 1 to 20 of 1 plus 2I over 20 times 2 over 20. Now 2 over 20 is a constant. It can be taken outside, and basically when we enter this into the calculator, we're going to need to say sum of a sequence. And remember, I is represented by x, so it'll be 1 plus 2x over 20. Excuse me, there was a square here. 2x over 20 squared, comma x for the variable, comma from 1 to 20 for the limits. And here's how I entered it into the calculator. And we're getting roughly 9.07 for that. So that's the estimate using 20 rectangles. And do you think the estimate is an overestimate since we are using the right endpoints and this happens to be an increasing function? Yes, this is a little bit of an overestimate. The correct answer should be a little bit less than that. And as we increase the number of rectangles, we would have a better and better approximation. Now let's do part B. Find the exact area under this curve. So for that, I'm going to start a new sheet and copy that A sub n to my new sheet. So A sub n was summation of, as I goes from 1 to, let's do in general n right now. So from 1 to n of 1 plus 2I over n squared times 2 over n. Okay, right off the bat, I can factor out that 2 over n, since it doesn't depend on I, and I can expand that binomial. 1 plus 1 squared is 1, 2 times the first and the second, that's 4I over n. The square of the second term, that's 4I squared over n squared. As I goes from 1 to 10. Now let's try to distribute our summation notation. So this will be summation of 1 plus summation of 4I over n plus summation of 4I squared over n squared. In each case, I is going from 1 to n. Now let's simplify it. This time I'm going to factor things outside of the summation sign. If something does not depend on I, it can be factored outside. By the way, summation of 1 is going to be just n. Remember, for a constant, you multiply with the upper limit, that constant. The next one, take out 4 over n. Okay, inside you're going to have summation of I from 1 to n, and take out 4 over n squared. Inside you have summation of I squared. In each case, I from 1 to n. Okay, let's distribute it 2 over n. As a matter of fact, before I distribute, I want to simplify my summations a little bit more. Summation of I is n times n plus 1 over 2. And in the last term, summation of I squared is n times n plus 1 times 2n plus 1 over 6. Okay, now distributing the 2 over n to the first term, we get a 2. To the second term, okay, on the top 2 times 4 is 8 times n plus 1 on the top. On the bottom, n squared times 2n. N squared times 2 rather. Distribute with the last term. So on the top we'll have 8 over n cubed plus the remaining stuff there, which was n times n plus 1 times 2n plus 1 all over 6. Okay. Now let's take a, this, remember this is your a sub n. To find area, you need to take the limit of the above as n goes to infinity. Let's see what we get. First term, the limit of a constant is itself. That's 2. Second term, on the top, the highest degree term is 8n squared. On the bottom, it is 2n squared. If you take the ratio of the leading coefficients, the limit will be 4. On the last one, if you multiply n times n plus 1 times 2n plus 1, the highest degree term there is going to be 2n cubed. And divide, don't forget there's an 8 also on the top and 6n cubed on the bottom. So it looks like we have 16 over 6. In other words, 8/3 as the limit of the last part. Again, degrees are equal, so we're taking ratio of the leading coefficients. We get 8/3. So we're saying that the correct answer under that curve over that given interval should be the sum of these three numbers. In other words, 6 plus 8/3. And for that, I'm getting 26/3. Which is 8.67. Now, this should make sense because earlier we did it for 20 rectangles, and we knew that was an overestimate, and that answer was about 9. So that this answer should make us feel good that, you know, at least it's in the close vicinity of that other answer we got. So the answer makes sense. That's always a good feeling. And next class, we're also going to learn another way to check your answer, and that will be the fundamental theorem of calculus, and that will make our jobs a lot easier. Just like with derivatives, there were shortcut rules. So these are going to be your shortcut rules for finding area. Okay, let's see if we can do one more setup. Yeah, this one let's just set up, and if you choose to, you can certainly simplify it as well. So set up an integral that represents the area under 3x squared plus 2 over the interval from 1 to 4. Let's begin with delta x, the base of each rectangle. The base is b minus a over n. In this case, that's 4 minus 1 over n, or 3 over n. X sub I, the partition points. You start with the left endpoint of your interval, and you keep adding multiples of your delta x, so 1 plus 3i over n. To get the heights, we plug in x sub I into the function. That'll be 3 times, remember this is the function now. So basically where you see x in there, take it out and replace it with your x sub I. So instead of x, I will write down 1 plus 3I over n squared plus 2. Putting all the pieces together, area using n rectangles will be summation of f of x sub I, the height of each rectangle that is, times delta x, the base of each rectangle, as I goes from 1 to n. We already know these individual components, we just are going to plug them in. So here we have f of x sub I, I might as well put it in square brackets, 3 times parentheses 1 plus 3I over n squared plus 2 multiplied by delta x. From up here, delta x was 3 over n. Of course, 3 over n does not depend on I, so that can be factored outside. So you can leave it, outside or inside either way. And from this point forward, again, for this question, I only intended to set it up. Area using n rectangles, these are really the right sums. And if you wanted to evaluate the exact sum, you would have to expand this out. Square your binomial, distribute the 3 over n, etc. And then finally take a limit as n goes to infinity. And if you want to do it using 20 rectangles, simply enter this quantity into the calculator. For n, you would put 20. For I, you would enter as x. And you would just do it numerically on the calculator. Okay, I'm going to leave you with an answer, so that in case you decide to continue this problem, you have a way to check your work. Just one moment, please. And the answer should be, for this question, 69, so you can check that out. Again, this material is a little bit heavy in the beginning, but problems are very repetitious. They always use the same ideas. So even though it looks very complicated maybe in the beginning, as you do several examples, you really can get a good understanding of this and a good skill at being able to do these questions. So do lots and lots of questions. So what's new, right?